Hello, we are going to start a series on the discussion on coordinate systems. To start with, we have the spherical and cylindrical coordinate system and also the kinematics that will be associated with it. Now, many problems in mathematical physics they exhibit a spherical or cylindrical symmetry. For example, the case of gravitational field of the Earth, that is of spherical symmetry. The waves that are excited by a stone which is thrown in water, that exhibits a cylindrical symmetry. Now these problems they can be dealt with by the coordinate system, the regular ones, that is the XYZ coordinate system, the rectangular coordinate system. Now it is usually not very convenient to use such a coordinate system in these processes. The reason for this is that the theory is usually much simpler when one selects a coordinate system with symmetry related to the ones that are exhibited. Now, it is for this reason that the spherical and cylindrical coordinate systems are introduced, and we are going to discuss about them in this video. We are going to discuss a part of it in this video, and this will be a series of some videos. So first of all, I'll be introducing the case of the spherical coordinates. So in case of spherical coordinates, first up, let me provide you with a diagram for comparison between the two coordinates. So first of all, we'll have the general case of x, y, and z coordinates. So these are the x. Well, let me take this one as x, this one as y, and this one as z. And we have a point with a position vector r. So this is the point. Let us say this point is P, and it has a position vector r. Now the position vector here is making an angle theta with respect to the z-axis, and thereafter its projection on the xy plane is going to be somewhat the case where we are having the angle with respect to the x-axis as phi and with respect to the y-axis as 90 minus phi. So these are the coordinates that we can consider at the moment. We have the two angles, we have the position vector, and then the rectangular coordinates x, y, z. Now from this figure, of course, you may be well aware that r, theta, and phi are the ones which contribute to that spherical coordinate system, and we can relate them. So we have the value of x to be equal to, as you can see from the figure, it will be r sine theta, which will be the line over here, this one, and then again if its projection is to be considered on the x-axis, then we have cosine of phi, and then for y we have r sine theta sine of phi, and finally we have the value of z to be equal to r cosine theta, because that's the projection of the r position vector on that z-axis. Now we will be using these expressions. So from these expressions, what can we get for the value of r? Now if we square both the sides of each of those equations and just add them up, what do we end with? We end up with something that is x squared plus y squared plus z squared on the left hand side, and on the right hand side what we get is r square can be taken completely outside, as the common term, and then we have sine square cosine square phi, sine square theta cosine square phi plus sine squared theta sine square phi plus we have the cosine square theta. Now if you add them up further, you can take the sine square out of as the common term for the first two values over here. From these two you can take sine square theta as the common term, and you have cosine square phi plus sine square phi, that goes to 1. So sine square theta, so this is r square sine square theta plus we have the cosine square theta, that again results in 1. So this is simply r square. So from this what we get to know is r simply is equal to, by magnitude of course, we are concerned about the magnitude only in this case. So r is simply equal to the root over of x squared plus y squared plus z squared. That's pretty straightforward considering the coordinates, the rectangular coordinates. Even in that we had the value that r is equal to, as you know, r is equal to x I cap. Supposedly this was projecting on a value of x over here. So this is x and this is y over here. This is x, and then this would be projecting over here as z. So the values, the magnitude are x, y and z. So x I cap plus y j cap or j hat you can say, and z k hat. So this is the value of the position vector. Now this z is for the measurement, of course, the magnitude. Now with these with this value obtained and this formula that we have for r, we can have a formula for theta as well. Now theta here will be equal to the cosine inverse of z over r modulus, of course, or we can write z over x squared plus y squared plus z squared all under root. And then we have the value of phi, which is equal to all in magnitude, of course. This is tangent inverse of y over x. So this is the value of r, theta and phi in terms of x and y, and this is just the magnitude. We are concerned about the vector form of it because we are going to deal with the coordinates, so we need to have the vectors over here. In order to obtain the vectors, if you look at this case over here from this formula, what we get is we have the unit vector supposedly. Now the unit vector along the x coordinate is I hat or I cap, and that is simply equal to, if you look at this, this is simply del r over del x, that is the partial derivative of the r vector with respect to x. Similarly, we have the unit vectors of j, that is along the y-axis, and k cap along the z-axis. They can be obtained in the same manner. So these are the unit vectors in the rectangular coordinate system. Now if we are to obtain the unit vector along the given along the spherical coordinate system, we follow the similar procedure. Now unit vectors by definition, also we have that unit vectors I hat is nothing but equal to the magnitude of the vector, we can take it as the vector x over the modulus of x. And also the same goes for the case of j and k, where they are the unit vectors. Many a times this is also written as x hat, so it's all the same, different notations and different texts, but we'll stick to that the general notation of I hat, j hat, and k hat. Now let me number those equations if because we'll be using them frequently. So this is let us say equation number 1, and this set represents the equation number, let us say we take it as 2 in common, but here we will take it as 2a, 2b, and 2c for our convenience. In its entirety, this will be equation 2. Now if we use those values of x, y, and z from the equation 2 in the first equation, so using 2 in 1, what do we get? So we get the value of r vector that will be equal to the value of x, that is r sine theta times of cosine phi times of I cap plus r sine theta sine phi j hat plus r cosine theta k cap. So that's the value of r in terms of the in terms of the spherical coordinate values. Now from the definition of unit vectors over here, I'll take it as we'll take this set as equation 3, similarly like 3a, 3b, and 3c, and we take this one as equation 4, and we'll be using this concept, so let me take that as 5. Now from that concept of equation 4, we have I cap to be equal to del r over del x. Similarly, we can have r cap, and that will be equal to del r vector over del r. And if we do that in this equation that we have, we take it as 6 now. So using that concept in equation 6, what we get is that we simply get rid of those r terms. So we have sine theta cosine phi times of I hat plus sine theta sine phi times of j hat and cosine theta k hat. So that's the value of r cap. What's important to see is that if this is a unit vector, its magnitude must be equal to 1. Well, if you square all those components, that is the component of I, j, and k, all those components are going to give you the value, all those components when squared and added are going to give you 1, because when they were added with r as the common term, they simply ended up with r over here, r squared in that case. So all of those components, when they are squared and they are added together, they are going to give you the value 1. So this is the unit vector for r in terms of the this is the position vector's unit component or unit vector, and they are in terms of the other values, that is theta and phi, and in terms of the rectangular coordinate. So we have established a relation between the unit vector in the spherical coordinate and the unit vector in the rectangular coordinate. Now we'll also look at the case where we will be obtaining the value of theta cap and phi cap. So let's do that. Now for theta, as you can see that for del r over del theta, we are going to have the value as provided, but the modulus is not equal to 1. So in order to get the modulus to be equal to 1, we simply divide that r that we have obtained onto the left hand side. So we have 1 over r times of the modulus of del r over del theta. That's now going to be equal to 1. So that means the unit vector of the theta coordinate, that is the theta hat, is going to be equal to 1 over r times of del r over del theta. And similarly, for the unit vector, that is the phi unit vector, we have phi hat to be equal to 1 over r sine theta del r over del phi. So that's the value that we obtain for all those unit vectors in the spherical polar coordinate system. Now with all of these available, we can formulate them in a matrix. Now in order to formulate them in a matrix form, we have r hat, and we arrange them in the column matrix form for I cap, j cap and k cap components. So if you remember, here we had for r hat, we had r sine theta cosine phi, followed by r sine theta sine phi and r cosine phi. So we write them in the column matrix form, that is sine theta cosine phi, then sine theta sine phi, and then we have cosine theta at the end. Similarly, we follow it up for the elements of the theta hat and phi hat, and they have been written. Now as you can see, we have got rid of the r terms that were multiplied in case of del r over del theta over here, because we had divided that r, so that's gone. That's no more a part of it. So all we have the component of I hat as cosine theta cosine phi, then cosine theta multiplied with sine phi, and then we have minus sine theta in case of theta hat. Now as in case of phi hat, because we have divided the 1 over r sine theta, so r and sine theta terms are going to be absent from that, and obviously the last term is simply 0. So those are the unit vectors, and they have been represented in the column matrix. Now if we may use these terms that were multiplied to the factors, or to those unit vectors of gradient terms. So here is the gradient term for del r over del theta, and we have del r over del phi. The common terms that were multiplied in these cases, the first being r, and in the second case it is r times of sine theta, which were usefully divided. And if you observe the first one as well, del r over del r, there is no such extra term, so the coefficient in that case is going to be 1. Now for future references, we are going to keep those factors which were divided with those equations, and we are going to name them as scale factors. We are going to just have them with us in case we will be needing them. So we represent them as h subscripted with r, that is 1, because the coefficient there was 1, and h theta is r, and we take h phi as r sine theta, and we just, for the time being, we keep them for any kind of future references. Now with the unit vectors available to us, we can however verify that r dot is going to be equal to theta theta dot, and that will also be equal to phi dot, the dot product of the unit vectors, and that is going to result in 1. And being the case, and obtaining the case of orthogonality, we have r hat dot product with theta hat, that is equal to r hat dot product with phi hat, and similarly the inner product of theta hat with phi hat, they are going to end up with a 0. And also we can successfully verify that r hat, when we do the cross product of r hat with theta hat, we end up with phi hat. Similarly, for theta hat cross product with phi hat, we have that to be equal to minus r hat, and then finally we have phi hat cross product with r hat, and that is theta hat. It's usually effective to remember these things. You can verify them with the formulas available, but the order is quite easy to remember if you remember the ordering of I hat, j hat and k hat. Remember, I, j, k, they were in the cyclic order, so I cross j would have given you a k, j cross k would have given you an I, and I cross and k cross I would have given you a j. So all of them positive. Anything in the counterclockwise sense, taken in the counterclockwise sense, would have ended in a negative sign. That is, j hat cross product with I hat would have given us minus k hat, that is negative of k hat. So the counterclockwise sense is negative, the clockwise sense is positive. So r, theta and phi would have taken that form, but it's only the case where for theta to phi, that is where the negative term comes up. So you have the cyclic approach, you can have that, but only over here this approach doesn't count. So from theta to phi you have a negative r over here. So that's an easy way, just in case you want to remember this cross product of these two unit vectors or these given unit vectors. Now again, considering these set of equations that we have just obtained, that is for the unit vector in the spherical coordinate system with respect to the unit vectors in the rectangular coordinate system, we can now represent them in this form. That is, we take the matrix form now. So this is some matrix M multiplied to I hat, j hat, k hat column vector, and if you can observe, we have the M, that is the square matrix 3 cross 3. We have the elements as sine theta, cosine phi, sine theta, sine phi, and cosine theta, followed by cosine theta, cosine phi, cosine theta, sine phi, and minus sine theta. Then we have minus sine phi, cosine phi, and a 0 to end. So this is the matrix M. So it's this expression that we have over here is a shorthand notation to the conversion that we have done, or the transformation that we have carried out from one coordinate frame to another coordinate frame, that is from the rectangular to the spherical coordinate system. Now let us take the case of a vector. Let us say the vector is u, and we have the value as u vector. We want to represent it, we want to express the u vector in terms of the spherical polar coordinate system, that is u r, the coefficient of the position vector, unit position vector, u theta the coefficient of the unit polar, and the u phi as the coefficient of the azimuthal unit vector. Now the vector obviously does not lose its form. In the case of the rectangular coordinate system, it would have been ux I hat plus uj or uy j hat and uz k hat. So these would have been the coordinates being ux, uy and uz, and the unit vectors in that frame or in that coordinate system, and this is the case in spherical polar system. So we are going to just establish a relation which is going to, now in case of unit vectors it was fine, we had the case of the r vector in that, so it's pretty simple. If we take the case of the unit vectors that we have just obtained, so what we get here is we simply represent this one as ur stays as such, and that is multiplied to r hat. Now r hat has the value which was given in the transformation in the previous page, that is down there. Yes, we had the value of r hat over there, so we are just going to multiply that r hat with ur that is present over here. So let's do that. We will be doing all of them one by one like this. Now we separate them in terms of the rectangular coordinates, just to compare, so that we can be able to compare with this factor over here. So those are, as you can see over there, with the left hand side being equal to u vector in both the cases, the bracketed terms over here, they will be giving you ux for the first bracket, uy for this next one, and uz for the third one. So these are the value of the coefficients with respect to coefficients in one frame with respect to the other frame that has been considered, and that would lead us to this. And if you observe this one, then this is nothing but the transpose of the M matrix that we had considered. If you look at that, sine theta cosine phi, sine theta sine phi, I'm reading it column wise, sine theta sine phi and cosine phi. And let's go back to the previous page where we had the matrix over there. Where's the previous page? Yes, right there. So we have sine theta cosine phi, sine theta sine phi, and cos theta. That was in the row form, and now this one is in the column form, the small correction in the theta cosine theta case. So this is the transpose of that matrix. Now if we wish to reach the goal that we were looking for, now if we have the transpose taken to the other side, so we have ur, u theta and u phi, that will be simply equal to the matrix transpose taken inverse, and here we have ux, uy and uz. Now we need not necessarily compute this inverse of this transpose. Now in case of orthogonal matrices, there's a useful property which tells us that for orthogonal matrices, or for an orthogonal matrix, in this case being M, we have M inverse to be equal to the transpose of M. Now the inverse, so M transpose, when taken inverse, it is simply the inverse of M, and that is nothing but equal to M. So what we get over here is simply the matrix itself. So we have ur, u theta and u phi to be equal to M times of ux, uy, uz. So this is the relation or the transformation that we were looking for in case of any given vector in the spherical coordinate form with respect to the rectangular coordinates. So that's all from this video. We'll be continuing with our discussion in this topic in the upcoming videos. Till then, thank you for watching.